So what I planned is to give sort of introduction to the subject of resource theories in quantum information theory, and sort of give an example of entanglement theory as a sort of an application of various sort of problems we look in the framework of general quantum resource theories. So firstly, let us start with the idea of quantum resource theories. So whenever you hear quantum resource theories, you basically it basically means a mathematical structure, which nowadays is basically used to study various quantum resources. For example, the well-known entanglement theory. After it kind of developed maybe in early 2000s, people realized that the structure of entanglement theory can be basically applied to study many other quantum resources, and this was the starting of this idea of resource theories. So after entanglement theory, many other quantum resources like quantum coherence has been studied in this framework of resource theories. And recently it has been, like, I don't know, probably like 7 years ago, it has been shown that athermality, it's basically sort of quantum thermodynamics, can be put into the framework of quantum resource theories. So over and all, this sort of gives a very rich mathematical framework to study various quantum phenomena which we are interested in. And when someone is studying quantum resource theories, one of the important problems which one is trying to solve is the problem of state transitions. So what do I mean by the problem of state transitions is, so I give you a state rho and a quantum state sigma, and one needs to know that if there exists a transformation between them. This is called the state transformation problem, and this is one of the basic problems which one is trying to study in the framework of resource theories. And what do I mean by these things? I will try to explain in the upcoming slides. So firstly, some basics. When I say quantum states, I mean by positive semi-definite operators. So every positive semi-definite operator is a unique quantum state. So, and what do I mean by positive semi-definite operators are basically these operators. So first of all, positive semi-definite operators are denoted by this notation, rho greater than or equal to 0. And additionally, quantum state should be positive semi-definite, and also trace of the quantum state or the trace of the positive semi-definite operator should be 1. And what do I mean by positive semi-definite is for example, a matrix rho is positive semi-definite if and only if it has to be Hermitian, and also all the eigenvalues should be greater than or equal to 0. So this I of rho is basically the vector of all the eigenvalues, and all the eigenvalues should be greater than or equal to 0. So if it satisfies these two properties, that it's Hermitian and it's all the eigenvalues are greater than or equal to 0, and the matrix is positive semi-definite. So additionally, quantum states also have this property that the trace of the matrix should be 1. So for example, if you take a matrix which is positive semi-definite, it means it follows these properties, and if the trace is 1, it's a valid quantum state. And what do I mean by quantum operations are basically CPTP maps. So what do I mean by CPTP maps is maps which are of this form. So for example, you have a quantum state rho, and if you want to transform it through a map epsilon, then this epsilon of rho should be given by a summation of cross operators. So it has to be represented by this form, since it's ki rho, ki dagger, and where you somehow this such that the ki dagger ki will sum up to identity. In fact, any transformation which has the first property that it can be expressed as a set of cross operators is called completely positive. And trace preserving is an additional property, which means that the summation of all these cross operators should be identity. So this is what I mean by CPTP maps, and these are basically the quantum operations. That means if you can arbitrarily write on a piece of paper, you can write an arbitrary transformation by choosing a set of cross operators which basically satisfy this normalization. That means the trace preserving condition. You can always go to the laboratory in principle and create a device which does this transformation. And similarly, if you do any arbitrary transformation in your experiment, you can always come and write on a piece of paper the cross operators of the transformation, and they have to sum up to identity. And this is what I mean by quantum operations. And one can extend this notion of quantum operations to something called probabilistic quantum operations. And these probabilistic quantum operations are also called as quantum measurements. So for example, if you do a measurement, let's assume your measurement has two outcomes, outcome 1 and 2. And the transformation of of the the transformation of the measurement outcome 1 happening is also can be given by a quantum operation. But this quantum operation will be probabilistic because there's a probability of getting 1 and the probability of getting 2. But if you just stick to 1, then it's a probabilistic quantum operation. And probabilistic quantum operations, or so-called quantum measurements, can be described in the following way. They should again have the CP property. That means they should be given as a summation of a set of cross operators. And additionally, this set of cross operators should not sum up to identity, but a matrix which is less than identity. And this, if you can write a transformation in this form, this is called a probabilistic quantum operation or a stochastic quantum operation. And the probability of happening of this outcome is given by the trace of this. And since the cross operators don't sum up to identity, but some operator which is less than identity, the trace is always between 0 and 1. And here since I said the summation of cross operators should be less than identity. What do I mean by a matrix less than identity is the following. So for example, if m is greater than or equal to n, this is basically equivalent to saying m minus n is a positive semi-definite operator. So basically here what I mean is this summation over cross operators minus identity, or identity minus summation over this cross operators, is a positive semi-definite operator. So any quantum operation which can be described in this way is called a quantum measurement or a stochastic or probabilistic quantum operation. And also if you have any questions in between, you can always interrupt me. Okay. So once we have this, I can describe what is a quantum resource theory. So a quantum resource theory necessarily basically means a set of two things. One is called free states, and another one is called free operations. If you have free states and free operations, and that means you defined a quantum resource theory. So whenever I say quantum resource theory, I basically mean a set of free states and a set of free operations. Now, what are these free states? So free states are basically a subset of total quantum states. So the set of all quantum states are basically a set of all positive operators which are trace 1. But if I take a subset of them and I can define them to be free states. So free states are, you can always choose a free states to be a subset of all quantum states. And usually it's assumed to be convex. So if it is convex, then usually your resource theory has some nice properties and stuff. So you want it to be convex because if you take a free state, if you take two free states probabilistically, like for example, with probability p, I take a free state rho, and with probability 1 minus p, I take another free state sigma. Then the free state I took will be a mixture of rho and sigma with probabilities p and 1 minus p. And this probabilistic mixing should also be a free state. It should not go out of the set of free states. That's what I mean by convex. And free operations are basically a subset of quantum operations which I can choose and define them as free operations. So if I want to define a resource theory, I need to do two things. I need to first define a set of free states, which are basically a subset of all quantum states, and a free operation, which are basically a subset of quantum operations. And once I define these two, I defined a quantum resource theory. So in any quantum resource theory, there is a restriction which these free states and free operations must follow. And the restriction is the following. If you take a free state and then you apply a free operation on it, you should get back a free state. So this is the only restriction which this set of free states and free operations must follow. That means if I take a free operation and I apply this free operation on any free state, you should never get a set which is outside the set of free states. So once I select the set of free states and free operations satisfying this restriction, we defined a valid quantum resource theory. And so this is what I mean by quantum resource theory. And this is a kind of a definition of quantum resource theories. So once we define a set of free states, we can define something called the set of resource non-generating operations. And what do I mean by set of resource non-generating operations is the following. So first, let's define a set of free states. Then we can define a set of all operations such that if you take this free operation and apply it on a free state, we get back a free state. That means so this set of operations is called RNG operations. So basically what I mean by RNG operations is, so if you take any CPDP map or a quantum operation which is outside the set of RNG operations, you can always find a free state such that you can generate a resource from there. So to be more clear, what do I mean by RNG operation? This is the largest set of quantum operations which preserve the set of free states. And that's what I mean by RNG operation. So this is the largest set of valid free operations one can choose once you choose a set of free states. Therefore, what one can do is one can choose a subset of RNG operations as free operations, and still you can define a valid resource theory. So once you choose a set of free states, you can choose a set of RNG operations, that is a maximal set of operations which map free states to free states, and then you can define a quantum resource theory, or you can use any subset of these RNG operations and still define a quantum resource theory. And how do you choose a set of free operations is usually motivated by some physical motivations, sort of a physical restrictions on your experimental apparatus and stuff. And this I'll show it to you as an example of entanglement theory in the following way. So let's see the case of classic entanglement.
Sorry.
Like
Hello.
Yeah.
There's a question.
Yeah, sure.
Sorry, I just wanted to make sure the question
Sure.
you operations don't have any result. They don't introduce hangover.
Actually, there's a delay in what you're saying, because the mic is somehow stopping in between. I couldn't understand your question exactly.
Can you bring up?
I'm just want to make sure why you choose approximate resource.
Why do I choose?
The operation that don't generate resource.
Yeah, that is a definition, no? So I choose a set of free states, and then the definitions I need to choose a set of free operations which map free states to free states.
Okay.
And these set of operations I call as free operations.
Okay.
So
I see.
Yeah, that's the definition.
Okay.
So
Thank you.
Yeah. So first I choose a set of free states, and then I choose a set of operations which map the free states to free states. So this set of operations, the largest set of such operations possible is called RNG operations. So these are the largest set of operations which map free states to free states. That means if I take any other operation which is not in the set of RNG, it will take at least one free state to another state which is not free.
So is this RNG also free operation?
Yeah, RNG is the largest set of free operations one can have.
Okay.
So if you take any quantum operation which is not in the set of RNG, there will be at least one free state which will map, there will be at least one free state which will go from free states to something else, which will go outside the set of free states. So the definition of RNG operations is the maximal set of the maximal set of operations following this property, that it maps free set to free set of states to free set of states. Yeah. So therefore, if you want to define a resource theory and you have a set of free states, the set of free operations can be RNG operations or a subset of RNG operations, because a subset of RNG operations also satisfy this property, because RNG is a larger set of operations satisfying this property, and you can always choose a subset as a subset of RNG and define as a set of free operations for your theory. And why does someone choose a subset? Why doesn't someone choose the entire set? Is motivated by physical principles, and that's what I'm going to show now. So let's take an example of bipartite entanglement. So the setting is, let's assume there are two parties, Alice and Bob, and they share quantum systems between them, quantum states between them. And the set of free states in bipartite entanglement theory are sets the states which don't have any entanglement. So these are the states which one can access for free. If there is Alice and Bob, they can generate these states which are separable. That means states which don't have any entanglement for free. So separable states are defined like this: the states which can be written in this form. So the states which can be written as a convex combination of this product states are basically called as separable states. So these are the states which don't have any entanglement, and these are the set of free states for entanglement theory. Once you define the set of free states, one can define this RNG operations, which are basically called the non-entangling operations. So non-entangling operations are basically the set of quantum operations which act on separable states and only generate separable states. That means you can never find a non-entangling operation which acts on a separable state and produces an entangled state. So these non-entangling operations are the largest set of quantum operations which map separable states to separable states. But you might notice that whenever people talk about bipartite entanglement, people are very much interested in things called local operations and classical communication, but people never talk about this non-entangling operations. The reason because local operations and classical communications, are physically motivated, in the sense that if these two parties, Alice and Bob, imagine they are very distant apart. For example, Alice is in New York and Bob is in somewhere in Europe. Then what they can do is they can only do local operations. They can do operations in their own lab. Additionally, what they can do is they can call on a telephone and share their measurement outcomes with each other. This is what they can do. Therefore, this set of local operations and classical communications is physically motivated. But these non-entangling operations are not quite physically motivated as these local operations and classical communications are. And the interesting point is this local operation classical communications form a subset of this neo operations, these non-entangling operations. Therefore, this can be chosen as a set of free operations for your theory, because any subset of this RNG operations can be chosen as a set of free operations for your theory. So therefore, whenever people talk about this theory of bipartite entanglement, the free states are the separable states, and the free operations usually are this LOCC operation, not this neo operations, because LOCC operations are more physically motivated. And yeah, therefore this is how one chooses the set of free operations when one defines a resource theory. Well, you can also define a resource theory by choosing set of free states as separable states and set of free operations as neo operations, and you can still define a valid resource theory. But people like to define LOCC operations as a set of free operations because it is nice to use because of this physical meaning of the operations. Yeah. So this is the first point I wanted to make, that whenever you define a resource theory, this is how someone defines a set of free operations and free states. So the thing you need to notice is once you define a set of free states and once you define a set of free operations, you saw that if you have this free operation, you can never generate. If you have this, for example, if you have this LOCC operations and you have a separable state, you can never generate an entangled state. You take a separable state, you apply LOCC transformation, you again end up in a separable state. Therefore, any entangled state is sort of a resource because you cannot generate it. If you're in a set of free states, you always lie there. You don't generate an entangled state. This is why the term resource theory comes from, because these other states which are not free states are called as resource states, because these are the states which you can never generate if you are in the set of free states. And and therefore the term resource theory. Similarly, one can also define the same spirit of resource non-genetic operations. One can also define the set of stochastic non-genetic operations. So when I say stochastic non-genetic operation, it has the same motivation in the sense that except that these are not CPTP map, but these are CP completely positive trace non-increasing maps. So these are quantum operations, quantum measurements. So this is sort of an extension to general resource theory framework you can have. We can also define this sort of stochastic free operations, which are basically that these operations are probabilistic operations. That means the cross operators don't sum up to identity, but they sum up to some operator which is less than identity. So they're probabilistic. But even probabilistically, they don't generate a resource. So if you have a free state row, then you apply a free operation, which is stochastic. You get a final state which you normalize, and it is a free state. So earlier, if I defined free operations for in the case of deterministic transformations, but here you can also extend it to stochastic transformations, where the probability is not 1, but you can still normalize and define it to be a valid quantum operation. But in this talk, I'll not talk about stochastic operation. I'll only talk about deterministic transformations. So this I'm just showing to you to see that people also work on these things called stochastic free operations. And similarly, one can also define a set of stochastic operations which are subset of stochastic RNG operations and define as free operations in their theory. Yeah. And once you have this, so as previously defined, we have a set of free states, and we have a set of free operations. And you saw that if you are in a free state, you always end up in a free state. Now, the states which are not free states, we can define as resource states. Now you can ask, how can you quantify the amount of resource? So for example, I give you a resource state, and then you want to know how much resource does it have. How can you quantify? And this one can do by the so-called measures of resources. So for example, if there's a measure of resource, that means it quantifies the amount of resource you have. What we want it to have, what we want is that it should have this, at least these two properties. And what are these two properties? The first property is that this measure, when applied on free states, should be 0. That means because free states don't have any resource, if you write down a valid measure of resource, it should give 0 for a set of free states. The second property is that the resource should not increase under free operations. So if you have a state, you apply free operation. So let's assume you have a state which has a resource, and if I apply a free operation, the resource should not increase. It can either stay the same or it can decrease, but it should never increase, because you should not generate resources for free. So that's the idea. That is basically the second condition, that under free operations, the resource is monotonically decreasing. So if you take a state rho, and if you quantify the resource as m of rho, then now you apply a free transformation on rho, and then you measure the resource, it should be lesser than before. So if you write down on a piece of paper, if you write down a resource measure which satisfies these two quantities, then it is a valid resource measure. If it violates one of these two, then you cannot say it as a resource measure. So this is the basic idea of measures of resources. And now one can ask, but well, how do you write down these quantities? There are various ways to write down these quantities, but okay, but there's one systematic way is to define the so-called distance-based measures. So, and what do I mean by distance-based measures is, so there are various distance-based quantifiers in quantum information theory. For example, you can have something called trace distance between two states, or fidelity, or one minus fidelity. So what do I want? So distance what do I mean by distance quantifier is basically it needs to satisfy the following properties. So a distance between the pair of two states, rho and sigma, should satisfy the following properties. That the distance between rho and rho should be 0, because they're the same states. And if you have two states, and if you apply a quantum operation, this is not necessarily a free operation. If you apply a quantum operation on both of the states, the distance should never increase. Should either stay the same or decrease. And this is the second property. So if you have a distance measure between two states which satisfy these two properties, you can always define a measure based on this distance. And this measure one can define by doing the following. Let's assume you have a set of free states and you have a resource state. You calculate the distance from your state rho prime to some arbitrary free state, and then minimize the distance over the set of free states. So you basically calculate the so if you want to know how much, if you want to define the resource of rho prime, what you do is you calculate the distance of rho prime to rho f, where rho f is a free state, and you minimize it over the set of free states. So for example, if the initial state is free, then you can always choose the same state, and you can measure the distance to the same state, so you'll get 0. And second, you can also it's also possible to prove that the second property also holds that the measures which are defined in this way doesn't increase under free operations. So basically, this gives a systematic way of defining resource measures. So what do you do is basically you take any distance quantifier, and then you minimize it over a set of free states, and this minimization is a resource measure. And what I mean by resource measure is it satisfies that for free states it's 0, and for resource states it doesn't increase under free operations. So as an example, I can show you a couple of resource measures. So for example, let's take 1 minus f, or where f is the fidelity. So fidelity between two quantum states. By fidelity, I mean this usual Ullmann fidelity. And this 1 minus f, you can take it as a resource measure. Sorry, a distance measure. That means this 1 minus, if you calculate this 1 minus fidelity of the same state with itself, it gives 0. And this 1 minus fidelity between two states doesn't increase under CPTP maps. So, and this condition of doesn't increasing or not increasing under CPTP maps is also called as data processing inequality. So this one minus f follows the data processing inequality, and it's also 0 for the if you take the same quantum state. And since it's a distance measure, you can always define a resource measure based on this distance measure. How can you define this? You can minimize this 1 minus f over the set of free states. So minimizing 1 minus f is basically equal to 1 minus maximizing of fidelity. And the resource measure, which is defined in this way, is called as a geometric measure. And the geometric measure is calculated for pure can be calculated. So you can always define a set of free states and free operations, and when you can always calculate this or at least define this geometric measure. This maximization can always not be computed analytically, but yeah, you can. But it's a convex optimization problem. So, but this is not the only way one can define these resource measures. For example, there is a so-called resource measure called generalized robustness, and how one defines this generalized robustness is in the following way. For example, if you want to know the robustness of rho, so the robustness of rho is defined as what is the minimum noise rho can tolerate before it loses all its resource and becomes a free state. So if you have a rho, the minimum noise is given by S. So what is the minimum amount of S such that if you mix it with some arbitrary state tau, where you also optimize it over this quantity over tau. So what is the minimum amount of noise rho can tolerate such that rho loses all its resource and becomes a free state? So here rho plus S tau by 1 plus S is a free state. And this minimum amount of noise rho can tolerate is called as robustness. And this robustness satisfies these two properties which a resource measure should satisfy. That means for free states it gives 0, and for any resource state it doesn't increase under free operations. So therefore, as you see, this generalized robustness is not exactly sort of a resource measure. I mean, later it has been proved that it can be written in form of a resource as a distance measure. But the idea is that there are various other measures in resource theories which are not basically this so-called distance-based measures. And now one can ask like what is the use of this doing this? Why does even one want to quantify the amount of resource? Like, is there any physical meaning to that? Well, the physical meaning is the following. The second property says that the resource measure doesn't increase under free operations. Therefore, if you have two states such that any arbitrary measure of sigma is greater than rho, then that shows that there cannot exist a free operation which takes from rho to sigma. Because if there exists a free operation which takes from rho to sigma, if there exists a free operation which takes from rho to sigma, then the resource measure of sigma should be less than or equal to resource measure of rho. That's what this property says. But since it's greater than the resource measure of rho, therefore there doesn't exist a deterministic transformation which can take from a deterministic free operation which takes from rho to sigma. So therefore, for example, if you define it, for example, let's take entanglement theory. You have a set of separable states of free states and LOCC operations. Now I give you two entangled states. I give you two entangled states, rho and sigma, and then you notice that actually there's a resource measure which is such that the resource measure of sigma is greater than the resource measure of rho. And once you notice it, you can say that there doesn't exist a LOCC transformation which takes you from rho to sigma. Therefore, this resource measure sort of give you no-go conditions on transformation of quantum states under free operations. So, because, for example, let's assume you have two pure states which are entangled. Let's take their psi and phi, and you can always calculate this so-called entanglement entropy, which is basically the local entropy of Alice. And this entanglement entropy is also a resource quantifier. And if the entanglement entropy of the state phi, if it is more than the entanglement entropy of the initial state, that means this sort of condition is holds, that the resource measure of the final state is greater than the resource measure of the initial state. Therefore, this says that there can never exist an LOCC transformation which takes you from psi to phi. And this is the sort of a main utility of this resource measures, so to sort of give this no-go conditions on transformations. Okay.
Hello, I have a.
Yeah, sure.
There are some different measures to by the resource. I was just wonder. So they are applying different situations or
You're saying why they are different measures? Yeah, because this resource measure is nothing physical. They are just mathematical objects. You can always define a resource measure satisfying these two properties. They're not something very physical. They're just, you can always define a mathematical quantity. What I mean by mathematical quantities, you can always define a map which takes a quantum state to a real number. And you can always define something like that satisfying these two properties.
So like there will be some situation, maybe one measure is better than another.
I wouldn't say better, but they can occur situations where the one measure. So let's take two measures, M1 and M2. One measure can say that measure of rho is greater than measure of sigma, but there can be some other measure which is valid. It can say that measure of sigma is greater than measure of rho. You see? Okay. So according to the first measure, rho has more resource, but according to the second measure, sigma has more resource. It can always occur these conditions. For example, in entanglement theory, you can always have situations where the von Neumann entropy of two states has this order, but entanglement negativity can have a different order. These situations can occur. So therefore, these measures of resource are not absolute. I mean, they don't carry any what to say, sort of a. I mean, you can always define a mathematical resource measure, and it will be a valid resource measure. The only place it is useful is
like in the case you say like two different states and using two different measures. Like the value would what?
The order differences. Yeah.
Then like in the next point, rho you can see free relation to transform into sigma.
No. It doesn't mean that. If the measure of rho is greater than measure of sigma, it doesn't mean rho can go to sigma. But if measure of rho is greater than measure of sigma, then it says that there can never exist a free operation which takes sigma to rho. So it gives a no-go condition, but it doesn't say that there exists a transformation. That's the difference. So for example, in this case, if you find a measure such that the measure of sigma is greater than measure of rho, then there can never exist a transformation from rho to sigma. But it doesn't say that there exists a transformation from sigma to rho. You see?
Okay.
Yeah, the opposite is not true.
Okay, thank you.
In this case, it just means you can find transformation for this measure or in general.
Can you just repeat the question, because somehow there's this the mic is stopping in between. I don't understand that. Hello? Can you hear me? Yeah, I can hear you now.
I mean, your next sentence means the transformation doesn't exist. Only for this measure or for general.
Yeah. So what this last sentence means, if you find a measure such that measure of sigma is greater than measure of rho, then that means there doesn't exist a free operation which takes you from rho to sigma. That's what it means. The opposite is not true. So for example, in this case, in this case, like the previous case, I explained to you that there can exist two measures, M1 and M2, such that M1 says that the measure of so M1 of rho is greater than M1 of sigma, but M2 of sigma is greater than M2 of rho. In this case, we can say that there doesn't exist a transformation which takes you from rho to sigma and also from sigma to rho. So these resource measures are basically used to give this no-go conditions, but they don't say anything about the transformation. If there exists a transformation or not, they don't have any information about that. They only have information to say that there doesn't exist a transformation. That's it.
Okay. Thank you.
Yeah. Thank you. So you can define infinitely different type of measures you want, but if you can find at least one measure such that the measure of sigma is greater than measure of rho, then you can say with certainty that there doesn't exist a free operation which takes you from rho to sigma. That is the idea.
I see. Thank you.
So these are So these resource measures are basically tools to identify which transitions are not possible, but they don't say anything about if the transition is possible or not in the other case.
Okay.
Yeah, this is the idea. So, but the question you asked, that does there exist a transformation between rho and sigma, is actually one of the central questions of quantum resource theories. So this question is called the question of deterministic transformation, which I will mention here. So here I'm actually showing what a deterministic transformation mean, but I'm using an example of entanglement theory so that you can see with a concrete example. So what do I mean by deterministic? The question of deterministic transformations is, let's say I have a pure entangled state psi, and I want to know if there exists an LHC transformation which takes psi to phi. So this is the question. And this sort of question you can also pose in general resource theories. Like if I have a state rho and have another state sigma, I want to know if there exists a free operation which takes you from rho to sigma. So, and this thing, it's not always solvable, but this thing is solved in many cases. For example, in this case of bipartite entanglement theory for pure states, this question has been solved for arbitrary dimensions. And the solution goes as follows. We know that so the psi AB and phi AB are basically this bipartite pure states shared between two parties, Alice and Bob. We know that there exists something called the Schmidt decomposition. And what I mean by Schmidt decomposition is any pure state shared between Alice and Bob. You can always write it in this way, where you get alpha i's are set of orthonormal bases, and beta i's are also a set of orthonormal bases. So alpha i's are basically a set of orthonormal bases on Alice's part, and beta i's are a set of orthonormal bases on Bob's Hilbert space. So any shared entangled state between Alice and Bob, you can always find a basis alpha I and beta I, and you can write it like this. And this root over lambda i's are called Schmidt coefficients, and these root over lambda i's are basically these lambda i's are basically positive numbers, and which sum up to 1. So you can view as this lambda i's as probabilities. So these lambda i's are basically positive numbers which basically sum up to 1. So this is called a Schmidt theorem, which basically says that if you have any quantum state, you can always find a basis alpha I and beta I, such that you can write it in this form. And so what do you need to do first is, you need to first write this psi and also phi in the Schmidt basis. Once you write in the Schmidt basis, you'll have so lambda i's are called as Schmidt coefficients. So you'll have the Schmidt coefficients of psi, which are given by the vector lambda prime of psi. So lambda prime of psi is basically the list of Schmidt coefficients. And I additionally assume that you need to order them such that when I write lambda prime, the vectors it's a vector of Schmidt coefficients such that it's an ordered vector. That means the largest Schmidt coefficient is on the top and the second largest is in the second, and like that. You basically order the Schmidt coefficients, and then you can write down this lambda prime. So the theorem says that there exists an LHC transformation which goes from psi to phi if and only if the Schmidt coefficients of phi majorize the Schmidt coefficients of psi. So I'll explain to you what I mean by this majorization. So if you find two for example, if you take two quantum states psi and phi, and if the Schmidt coefficients of phi majorize Schmidt coefficient of psi, then there always exists a free operation. That means there always exists an LHC transformation which takes you from psi to phi. Similarly, if you have two vectors, two pure states, such that the Schmidt coefficients don't satisfy this property, then there cannot exist an LOC transformation which takes you from psi to phi. So therefore, this gives a complete solution of this problem of deterministic transformation for pure entangled states under LOCC. So now let's see what this majorization means. So first I said you need to find out the Schmidt coefficients, and then you need to order them, and then you can find this vector lambda prime. Now, if the Schmidt coefficients of phi majorize the Schmidt coefficient of psi, that basically means that the first Schmidt coefficient, I mean the largest Schmidt coefficient of phi, is greater than or equal to the largest Schmidt coefficient of psi, and the sum of the first two Schmidt coefficients of phi are greater than or equal to the sum of the first two Schmidt coefficients of psi. Similarly, the sum of first three Schmidt coefficients of phi are greater than sum of the first three Schmidt coefficients of psi, and the list goes on until n. So the last inequality will be 1 is greater than or equal to 1. The last inequality is trivial, because if you sum all the Schmidt coefficients, you'll get 1, because they are like probabilities. So if all these conditions are satisfied, it basically means that the Schmidt coefficients of phi majorize the Schmidt coefficients of psi. And if the Schmidt coefficients of phi majorize Schmidt coefficients of psi, then there exists an LOCC transformation which takes you from psi to phi.
Sorry.
Yeah.
I have why majorization in this direction is not active. Because if you
can you repeat
this free operation LOCC, it means that for all measures, measure I will larger than.
Yes, that's what it exactly means. Yeah.
So it means for larger eigenvalue, it means the measure will small.
Not just the largest eigenvalue. The largest eigenvalue should be greater than this, but also the sum of the first two eigenvalues and some of the first three eigenvalues should also be in the same order. No. So if all these conditions are true, then you write any arbitrary measure of psi, it will be greater than the measure of phi.
Okay.
For any arbitrary measure, because you can never find a measure which is for which phi, the measure of phi is greater than measure of psi, because if it is true, then it's a contradiction, no?
Mm-hmm.
So yeah, that's actually true, that you write any arbitrary entanglement measure, the entanglement measure of phi will always be smaller than the entanglement measure of psi for any arbitrary measure.
So it's the the eigenvalue is larger. Smaller.
No, what do you mean by eigenvalue? You mean the eigenvalue of the local state?
Lambda. I mean the larger eigenvalue corresponds to large measure or smaller measure.
No. It doesn't directly correspond like that. But for example, you can see in the following way. So this transition holds if these conditions are true, no?
Yes.
You can also define the largest eigenvalue to be an entanglement measure, because it always decreases under deterministic transformations. You see, similarly, the sum of the first two Schmidt coefficients, you can also define it to be an entanglement measure, because it also decreases under free operations. Similarly, the sum of first three eigenvalues, or so the sum of first three Schmidt coefficients, you can also define it to be an entanglement measure, because it also decreases under free operations. But any of these conditions will not say if a transition is possible or not. So the list of all these conditions gives a complete characterization of these deterministic transformations.
Oh, okay. Thank you.
But but if you find out two vectors such that and then you order them such that I mean, in fact, you can never find two Schmidt vectors such that the eigenvalues of this vector are always greater than this, because they need to sum up to 1, no? So somewhere they have to decrease to sum up to 1. So, but these are the conditions which completely determine the transition law for two-qubit entanglement theory. Oh, sorry, for bipartite entanglement theory.
Okay.
For arbitrary dimensions.
Okay.
Yeah. So as you see, like for finding some arbitrary measures will not help you to find if there exists a transformation or not, but they are just to restrict the possibility of transformations. But this is one case where one can also solve this question of deterministic transformations. That means one can also find the complete set of conditions which which show that if transformation is possible or not. So this is a question of deterministic transformations. Next, one can move to something called asymptotic transformations under LOCC. So this is a slightly different criteria. So when I say deterministic transformations, for example, if I have a rho and if I have a sigma, if I say that there exists a deterministic transformation, if there exists a free operation which takes you from rho to sigma, but asymptotic transformations are defined in a certain in a slightly different way. For example, again, let us stick to LOCC operations. So if there exists for example, let's take n copies of rho, and if I want to know if n copies of rho can be transformed to n copies of to sigma with a rate r. With a rate r, that means per copy of rho, if you can get r copies of sigma. If this is possible, that basically means that so if there exists an asymptotic LOCC transformation which takes n copies of rho to n r copies of sigma, it basically means that there exists an LOCC operation which takes you from rho n to this gamma, such that the distance of gamma to the sigma nr is less than epsilon. This epsilon can be made arbitrarily small as n tends to infinity. So to put it in a better way, what do I mean is, if I say there exists an asymptotic transformation which takes rho to r copies of sigma, but if I say that there exists a transformation which takes you from, so let's take r to be 2. So if I say there exists a transformation which takes rho to 2 copies of sigma, what do I mean is, you cannot transform rho to 2 copies of sigma. If you transform rho to 2 copies of sigma, you'll end up with an error. Similarly, you cannot transform 2 copies of rho to 4 copies of sigma. Again, you'll end up in an error, but this error will be smaller than the first case where you transform 1 copy of rho to 2 copies of sigma. So therefore, you cannot transform n copies of rho to 2n copies of sigma, because there will be an error. But this error can be made arbitrarily small by choosing this n as large as you want. By choosing a larger value of n, you can make this error as small as you want. So that's what I mean by asymptotic transformations. So in a more simpler case, let's take r equal to 1. That basically means that there exists an asymptotic transformation which takes rho to sigma. That basically means that you cannot transform rho to sigma. So if you try to transform from rho to sigma, you'll end up with an error. But you can make this error arbitrarily small by choosing a large number of copies of rho. So if you take million copies of rho, you can go to millions of copies of sigma with a tiny error. Similarly, you can take 10 million copies of rho and convert into 10 million copies of sigma, and you can make the error even smaller. So this is what I call as asymptotic transformations. And this is sort of another sort of state transformation which are studied in the quantum resource theories. So in the special case of entanglement theory, if n copies, if there exists an asymptotic LOCC transformation which takes n copies of rho to rn copies of sigma, it basically means that you can transform n copies of rho with a LOCC operation to some shaped gamma, so that the distance between gamma and this n copies of sigma is less than epsilon. That means the error is less than epsilon, and this epsilon can be made arbitrarily small by choosing n as large as you want, by choosing a large enough n. That's what I mean by asymptotic transformations. Let's see a more simpler case. So okay, let's first define what is called as asymptotic rate. So what is the maximum R you can achieve such that these conditions are satisfied is called as asymptotic rate. And let's see a special case. Let's see again the simple case of pure entanglement under LOCC. Now, if the rate of transformation from psi to phi is given by the let's put it in a nicer words. So the optimal rate of transformation between psi to phi is given by the ratio of entanglement entropies. With the entanglement entropy of psi is basically defined in the following way. Entanglement entropy of psi is basically, you have a bipartite pure state psi, you trace out the part of Bob, you end up with density matrix of Alice, and calculate the one-number entropy of Alice. And this is called the entanglement entropy. So if you have two pure states, psi and phi, you can calculate the entanglement entropy of psi, and also you can calculate the entanglement entropy of phi and take the ratio of it. And this gives the asymptotic rate of transformation. That basically means that you can always choose n copies of psi and go to n times r copies of phi by doing LOCC. But this happens with an error. But the idea is that you can always make this error as small as you want by choosing n very large. So I give you a small error, and once I give you a small error, you can choose a large enough n such that n copies of psi go to n times r copies of phi with error which is given by you. So therefore, given any error, you can always choose a very big n such that there exists a transformation which takes you from psi n copies of psi to n times r copies of phi. And the optimal possible rate is given by the ratio of one number entropies. So therefore, if you choose any rate which is more than this, then you cannot do this transformation. That means you can never choose a for a very small epsilon. You can always not choose a very small, very big n such that the error is less than that. At some point, you'll hit the bound that you cannot suppress error more than that. So if you choose a rate which is given by more than this, then you can never suppress an error beyond a certain value. But if you choose a rate which is given by this or less than that, you can always suppress the error to arbitrary smaller values. So as an example, if you take two states, psi and phi, such that entanglement entropy of psi is greater than entanglement entropy of phi, that basically means that the rate is greater than or equal to 1. Since the rate is greater than or equal to 1, you can always go from n copies of psi to n copies of phi asymptotically. That basically means that there exists an asymptotic LOCC transformation which takes from psi to phi. So it's a way of saying that. So this asymptotic transformations are sort of a weaker constraints than deterministic transformations. So there can exist situations where, so for example, let's take this following example. Let's take the example where you have two states, two pure states, psi and phi, such that the entanglement entropy of psi is greater than or equal to entanglement entropy of phi, which basically says that there exists an asymptotic transformation which takes you from psi to phi. But there might not exist an LOCC transformation which takes one copy of psi to one copy of phi. This might not be possible because the decrease of entanglement, the decrease in entanglement entropy doesn't say that the majorization condition holds. So this majorization condition is a stricter condition than entanglement entropy. So therefore, you can have conditions where this majorization condition doesn't hold. Therefore, psi cannot be transformed to phi with LOCC, but the entropy of psi can be less than entropy of phi. Therefore, there can exist an asymptotic LOCC which transforms psi to phi. So this is the key point. So the main punchline is asymptotic transformations. Asymptotic put a weaker constraint than deterministic, the one-shot deterministic transformations or the one-copy deterministic transformations. So this is the first. So this is the first operational meaning of entropy which was given in the form of this asymptotic transformations, and it's also kind of intuitive, because whenever even when you talk about thermodynamics, entropy is a thermodynamic quantity. Sort of it gives you it describes your physical system when you have large number of copies, and that's what it kind of means. When you have large number of pure states, then the transformation loss is kind of sort of given by the entanglement entropy. But if you have one pure state, then entropy doesn't play much role. It's given by this majorization relations. So this sort of gives an operational meaning of what this one number entropy is. It's sort of so it gives a transition loss when you have large number of copies. Now again we come back to this this question of deterministic transformation. We have one copy of psi going to one copy of phi, and now I'll show you some funny situation. So these sort of transformations are called catalytic transformations. So these sort of things can be defined in general resource theory, but again I'm showing you an example of entanglement theory, how this works. So consider two states, psi and phi, such that the Schmidt coefficients of phi are not majorized by Schmidt coefficient. So this condition doesn't hold. That basically means the Schmidt coefficients of phi don't majorize Schmidt coefficients of psi. Therefore, there doesn't exist an LOCC transformation which takes you from psi to phi. But there can exist situations where you can have an additional pure state which you can attach, which Alice and Bob can share, which is called tau. I define it to be a catalyst, such that psi tensor phi goes to phi tensor. Psi tensor tau goes to phi tensor tau. If you see, tau is preserved in this. So tau doesn't change, and psi goes to phi. So therefore, there were two pure states which such that the transformation is not possible. But suddenly now the transformation is possible if you have an additional system which is called a catalyst, So catalyst is basically the name, no? The constraint is that the catalyst should not change. Therefore, you're not utilizing the resource of the catalyst. And this was first noticed by Plenio and co-authors in this PRL in 1999. And this was very funny because somehow it felt that you cannot transform psi to phi, but suddenly if you have, you can always choose a, sometimes you can always choose a an additional pure entangled state, which makes the transition possible, and the pure entangled state is preserved. So therefore, you can use it again and again you want. And these sort of transformations are called as catalytic transformations. So note that here the catalyst remains exactly unchanged, and therefore it can be again used to paint the procedure. And I'll also note that even this sort of transformations are not always possible, but there exist certain situations where an LHC transformation is not possible, but you can have a catalytic LHC transformation. So that's the idea. Now you can ask a general question. You have two arbitrary states, rho and sigma, and you have additional access to a catalyst tau. Then I want to know, when is this LHC transformation possible? And let's assume rho and sigma are pure states, like always, no? Like always we assume this talk. Let's assume this rho and sigma are also pure states. And now we want to ask if this sort of transition is possible or not. And this sort of question is also answered before, has been answered in this paper in I think early 2000s. And this sort of transformations are called catalytic transformations. But one sort of difficulty is if I give you two arbitrary pure states psi and phi, and if I want you to know if there exists a catalytic transformation between them, then one needs to, in principle, in the worst case, one has to check infinite number of conditions in order to know if a catalytic transformation is possible or not. Therefore, this sort of transformations are not easy to check. I mean, if there exists a deterministic transformation, then there of course exists a catalytic transformation. But let's assume there doesn't exist a deterministic transformation. Like there doesn't exist transformation of this kind, and if you want to know if there exists a catalytic transformation or not, or if there exists a catalytic transformation or not, then in the worst case one has to check like infinite set of this infinite set of conditions are given by the so-called NE entropies, which I'm not going to details, but yeah, one needs to kind of check all these infinite conditions to make sure that if there exists a catalytic transformation to go from rho to sigma, and this is not an easy condition to check. So what happened in recent times is one sort of people started to make this condition a bit more weaker. So now I define something called correlated catalytic transformation, again in the framework of LOCC. It's sort of a bit funny, but it carries the same motivation as before. So if there exists a correlated catalytic transformation which takes from rho to sigma, it basically means that you have a rho, you can append a catalyst tau, and you can do an LOCC transformation and end up in mu, and a final state mu, such that if you trace out the system, the catalyst should remain exactly unchanged. This is the exact same condition as before, that the catalyst should remain exactly unchanged. So the difference between the previous approach and this approach is, in the previous approach, the catalyst is exactly decoupled from the system initially and also finally. So therefore, there are no correlations between the system and catalyst. But here in the final state, the system and catalyst are correlated. The catalyst remains exactly unchanged, but there are correlations between system and catalyst. So that's why we call them as correlated catalytic transformations. And here we want the catalyst to be exactly unchanged because we want to use it again and again, no? Because that's why we want to make sure we are not utilizing any resource of the catalyst, and that's why we want to have that the catalyst remains exactly the same. And the second condition says that the correlations can be made arbitrarily small. That means you can choose if I say that the correlations can be measured by the so-called trace distance between the state and the product state, which I'm not going to technical this, but so if I say that the correlation should be smaller than epsilon, you can always choose a catalyst such that the final correlations are smaller than that epsilon. But still, there are some correlations. And this is what I call as correlated catalysis. So this correlated catalysis is sort of a weaker constraint than catalysis, but still carries the main motives of the so-called catalysis. And one can ask, why are you even looking at it? Why are you even looking at this correlated catalysis? And the answer is the following. And this is a nice result. It basically says that a pure state psi can be converted to pure state phi through correlated catalysis if and only if the entanglement entropy of psi is greater than or equal to the entanglement entropy of psi. So therefore, earlier, if I wanted to know if psi can be transferred to phi by catalysis, one needs to check infinite conditions which are given by Renyi entropies, and well, they are messy. But once you allow correlation between the system and catalyst, all these conditions basically collapse to just one condition, which is basically the entropy. And it's even nicer in the other way also, because entropy, as you've seen from traditionally, it has been looked as an asymptotic quantity. It only governs the laws of nature when things are, when you have a lot of systems, when you have asymptotically, when you have like a million copies, then the transitions are basically described by entropy, entanglement entropy. But here you see that if you have two states, just psi and phi, and if you allow a catalyst which can be correlated, then the transformation between psi and phi are basically governed by the entanglement entropy. So if I give you two states, psi and phi, as the entanglement entropy of psi is greater than or equal to the entanglement entropy of phi, you can always choose a catalyst and a LOCC transformation which takes you from psi to phi. These sort of transformations are called correlated LOCs, catalytic LOCC transformations, or correlated catalytic LOCC transformations. And also this can be defined by other resource theories as well. But I'm just giving an example of LOCC operations to give you a feel of resource theories. And therefore, this gives a operational meaning of entanglement entropy in a single copy regime, because there was an operational meaning of entanglement entropy, but this was an asymptotic regime where you have large number of copies. But this gives the meaning of entropy in a single copy regime as well. And yeah, this is the final slide with this in my talk. Yeah, if you have any questions, you can ask me.
Okay, thank you for the nice talk. Is there any question? Is there any question?
What's the final goal of quantum result? Is there real optimal theorem, right?
I'm sorry, but again, there is this disturbance with the mic. The mic is stopping in between. Maybe I cannot hear the question properly.